Does that make sense? Okay. Good. Do you guys want the good news or the bad news?
Bad news.
Bad news.
The bad news? Okay. There's never been a time when there was not a question on the final exam that said there was always a question on the final exam that said, explain the buddy system. Okay. Okay, so that's the bad news. The good news is, okay, it's the same steps repeated over and over again. Okay, we only have to look at the cue above in order to get one to break in half. When we break it in half, we need to remember what was the left and what was the right in case we need to move those blocks up and make them a bigger block on the cue we got them from. Okay, but we can find them by doing exclusive ORs. Blindingly fast operations. Okay. Questions?
You said explain, but how about you demonstrate for the final exam?
I will demonstrate will require you to actually write a program.
But I don't know if you have to do the
Well, you'll have to tell me about it, sure. Okay. That's just the explain. How does it work? Okay. So, questions about this? What if I were to ask you, why is it a constant time algorithm? How many of you could answer that? How many of you know we talked about that, but I've already forgotten the answer? Okay, that does happen. Remember now that our searches for that block is constant time because we only have to search the cues, not all the blocks. Okay, there's a fixed number of cues regardless of how many entries we have. So it becomes constant time. Now, if we go all the way to the top and it says, hey, there's nothing above me, then what we could do is say, all right, everybody stop, all your lower cues just start coalescing. Notice how we have that latency. We just jumped in there. Everybody stop. Nobody do anything. We're going to go off and coalesce. Okay? We kind of want to avoid that. So instead, we're going to have a background process running that's going to periodically look at the cues. Conceptually, the cues are going to do it themselves, but in an implementation thing, we run what's called a daemon in the background. So, the systems administrator, when they get their machine, it arrives pre-configured with about how many blocks do we want to have on each cue. Okay? And that's just something the operating system designer set up as a default. It turns out that in operating systems such as Solaris, you can actually set the defaults yourself. I don't think you can in Linux. Now, so we're pre-populating the queues, because otherwise the first time we go to allocate something, no matter how small it is, we're going to have to do worst case and go to the largest queue. Right? So instead we're going to pre-populate. Now each queue has associated with it two values, and they're called watermarks. Okay, and we'll see watermarks when we talk about paging as well. We have a low watermark and a high watermark. The low watermark says if we get below this value, we don't have enough blocks. Tell the queue below us to start coalescing. Okay? And if it doesn't have enough blocks to do the coalescing, it needs to ask the one below it to do the coalescing. And if that one doesn't have enough, it's going to percolate down. And eventually, if there is one available, it will percolate up to you. Okay? So the goal here is that when someone comes in and we say, hey, do you have a block for me? If we could build a block from the stuff that's below us, we've already done it. Now, as it turns out, that at some point we don't want to coalesce absolutely everything. We get to the high water mark, it's going to say that's enough. We've got enough stuff here. All right? So that's coalescing from below. it turns out that we can also ask to split from above. So if I hit the low water mark, I can say, hey, queue above me, give me a block. Give me a couple blocks. Okay? I'm not allocating, so when I get them, I'll put them both on my queue. And it can continue to do the same thing, going up. All right? Usually we do the splitting. When we get to the low water mark, we ask for splitting first before we go into coalescing. But that's just an algorithmic choice. You can do it either way. Okay? But that increases dramatically the following scenario, which is when your request comes in, we saw before, there will be a block there. So you have the vast majority of the time, when a request comes in to allocate memory, you only have to check one queue. The only way that would get you into trouble, okay, that is that you wouldn't check just one queue, is in the following scenario. Okay? Your queue is popular. You're doing lots and lots of allocations faster than you can repopulate it. So you run out. But you might be able to repopulate it, so now you have to go and ask all the queues to coalesce or split. Okay, and that becomes takes longer. Okay, so it's not optimal at that particular point in time. Okay, and that's it. So what operating system designers tend to do when they pre-populate these lists at boot time is the sizes that from their studies show are popular, they put more items on the list. The ones that aren't very popular, they put less items on the list. They might even put 0 on a list. Because it's like, if anyone ever asks for this oddball size, okay, it's an oddball, we're willing to make them pay the penalty of getting one from the bigger queue. Okay. They pay, 100 nanoseconds delay. Right? Which could actually matter. Could actually matter. So we expect normal running time to only look at one queue and have the size that we're looking for. Okay. But we could have, almost always we know we're going to have internal fragmentation because we almost never ask for a power of 2. Curious side note of this is, let's say 1K is the minimum block size. Is you ready to play this game? How many of you have ever allocated, size of int? Anyone ever done that? Okay. How many bytes? 4, but the minimum allocation is 1024. So it turns out that if you got a request that's smaller than the smallest queue, you could have more internal fragmentation. Okay. And it turns out there's ways that we can manage that, but it's beyond what we're talking about. It'd be sort of an advanced malloc trick that we would do. But that's the place where we could have more internal fragmentation than 49.9%. Okay.
Can you just have like imaginary unpopulated queues going all the way down to like 2 or 0?
Sure.
For size?
You could do that. I mean, at some point, it's a point of diminishing returns, though. I personally, when I describe this, I like to start at like 8 bytes. In the 64-bit architecture, that's the size of an int. If someone wants a char, we're just going to waste 7 bytes on it. Okay, we're still wasting more than 50% of the space, though. Right? Yeah. So unless we go all the way down to a char, okay, you see the nutty extremes we can go to here? So we have to find, as designers, we have to find the happy medium. So the OS designers, they're going to run millions and millions of tests simulating loads and actually figuring out which queues are being used the most, which ones are not being used at all, and then sort of ranking them in terms of popularity. Okay? So there's quite a bit of this that goes on. So let's say you're a big user of Linux, let's say Red Hat. Let's just make something up. Let's say, you guys know about Mentor Graphics? Yeah. Do ECAD tools down in Wilsonville? They have, their tools are huge. Okay, they allocate memory all over the place. I used to write software to modify those tools to use at Boeing. And so I'm familiar with them. They do just massive amounts of allocations and frees all over the place. All right? So it turns out that they're representative. So what Linux could do, let's say they're using Linux Red Hat. I don't know what they're using. I think they're using IBM now. But let's say we go out there and they say, okay, here's an instrumented operating system. We want you to run all your tools on it, collect the data files and send them back to us. Or more likely, what they're going to do is buy a couple Mentor Graphics workstations, get some consultants that actually know how to actually make them sing and dance and all that kind of stuff, and then run them in-house, collect all that Q data, and then analyze it. They're going to do that with thousands of companies. Okay? So it turns out if they just go off and hire a consultant to run their tests, Mentor Graphics will never know. Okay? When I was at Boeing, we used Mentor Graphics. We wrote tools for board level CAD, so our software would just lay out the boards and all that, so you could build your circuit boards. That's part of what we did. And it turned out that we had a board that was 3.5 feet tall. What was it? 3 feet wide. Okay, one board. And you had to print it out so you could actually look at the traces and make sure that things were working. And it turned out that for almost 20 years, Mentor Graphics used that to check the print drive. It was the biggest thing anyone had ever tried to print. Okay, that board we're part of a simulator that we worked on for the B-1B bomber. So that was the B-1B Visual Flight Simulator. So memory allocation schemes are checked with Webster's mass destruction. Okay, now that I've made everybody happy. So, questions about this, how it comes together, what's going on here. Please read Amy's document.
I was wondering if there was any special action that you took when it hit high watermark, or if it just stopped.
It's high watermark, it just cancels all its requests. You know, because conceptually what it's going to do, when it gets to the low watermark, it's like, give me one. And if it still hasn't hit the low watermark, it's going to give me another one. But what it could do is it could say, hey, you know, if I don't want to be bouncing off the low watermark all the time, I want to be anywhere between the low watermark and the high watermark is my sweet spot. Okay. Someone could write an algorithm where it says, turn everything into a 4K block. Right, and that would probably be inefficient because anything else would either have to start doing coalescing or splitting. So we want to avoid that. So we create these high and low watermarks. And they're just there for us to tell our algorithm when to stop or when to start.
Are the low watermarks a function of how much free space you have? Because theoretically, if you use up most of your space, then
It's actually that statistics where we say how popular this queue is. The more popular the queue, the more blocks we want to have on it at any particular point in time, which means it'll be a higher low water mark. Okay. Usually the high water mark is probably going to be set, except for a queue that's not really used, it's going to be set to be something the same across all of them conceptually. It's like, you know, if I've got more than 45 blocks, that's just kind of a waste because statistically the groups that come in and ask me for a massive amount of stuff, the tests show we never get more than 35 in such a small period of time that we can't ask the other queues to give us blocks.
yeah, but if you're like running out of memory, then everyone's going to be.
If you're running out of memory, all right, you got bigger problems than you need to coalesce.
There'll be something else to be like. No.
So yeah, there's a point. If I don't have any memory, yeah, it's going to be worst case every single time for us to return a null that says, nope, sorry, no memory. Okay. Or if we have nothing we can coalesce at a lower list, and it comes in, and there's nothing on the higher queues, yeah, it's going to be worst case for us to come back and say, no, there's nothing there for you. Okay. But those cases say we're using most of our memory at that particular point. Unless, of course, someone's trying to do something like malloc 4 gigabytes, all right, which you can do, you know, malloc 4 gigabytes and then just start walking through the memory and watch the performance on Babbage. Other questions? Okay. Managing free space is hard. Okay. Managing free space in these blocks are really quite hard. How would you like to get rid of all of that?
I would.
Okay. So, remember our virtual address space? What was the beautiful thing about our virtual address space? It's contiguous. But what we've been seeing with segmentation is that the allocation of physical memory behind it doesn't have to be contiguous. Okay. What if we could take that to an extreme and say, you know, however much memory you want, I can make it look contiguous in your address space, all you want. It doesn't have to be contiguous, even at the byte level, where it's in physical memory. In which case, all I have to worry about is the allocation chunk coming out of malloc. Malloc will allocate in your space, in your virtual address space, and say, okay, yep, you got it. And then when you need the backing store, the physical memory, we'll just allocate it on demand. But what would be the right size? Because allocating things a byte at a time. Okay, you want 10,000 bytes. I need to go find 10,000 different 1 byte segments in memory. That's not going to get you a PhD. But what if we were to find a size that worked out really, really well? Now, it's one of those, most of the time, this is great. Okay? Notice I said a size, not a set of sizes. Okay. If they happen to be a power of 2, those groups, what do we know? External fragmentation just one way again, didn't it? And if they're not too big, it turns out internal fragmentation is going to be highly bounded. And it's actually been bounded in a clever way. We have these chunks, we're going to call them pages, because they look just like a page in a book. They're all the same size. And as your heap needs room, you just keep filling up those pages. Okay. All right. And so we almost never allocate exactly a power of 2. So we're going to have some leftover space, but it's only going to be in 1 page. Okay? And the worst case is we're only using 1 byte out of it. The best case is we're using all of them, which means the average case is there's a 1 and a 2 involved in this. Half. Statistically, it's going to be half. So let's say we pick a 4K page. Statistically, in our code and our stack and our heap, each one of those pages that back it, on average, have 1/2 of a page of internal fragmentation, no matter how big the process is. It could be 700 petabytes. Okay, but on average, it's going to waste 2K. Process gets bigger, the percentage of the internal fragmentation goes down. And worst case, it's just 1 byte short of 4K, right? Now, if you only need a 1/4 page for your process, which is rare, it'd be some pretty amazing hand-tuned assembly code. But if that's all you need, well, yeah, then your statistics look like I'm wasting more than 50%. But it turns out that the statistics that we talked about before about amount of space that's in use, it's usually closer to 100K. So 4K is in general, we're closer to 100K. So if we waste 2K out of 100K, that fragmentation, how much fragmentation do we have in our system? 2%? Better than 49.9? By a long way. Okay? The bigger our process, the smaller that number becomes. Because the actual amount, the actual number of bytes, worst case, is 4K minus 1. That is a fixed value. Okay. Kind of cool? Guess what we're going to spend the entire next class talking about? How to do this. Okay. In fact, we're going to spend 1.5 classes talking about it. All right. What do you think we're going to need 1.5 classes to talk about it? It's really cool optimization, but with cool features usually comes complex algorithms. And the complex algorithms usually come with higher latency. So we're going to find a way to get this really cool feature and at the same time make it optimal in terms of speed. Has anybody read ahead? Does anybody know how we're going to fix this problem of latency? Caches to the rescue. Okay. We're going to do a special one just for address translation. So this is not a data cache. This is address translation. And because we're doing address translation, there's going to be a translation device. And for historical reasons, it's called the translation look-aside buffer. Okay? The look-aside is weird, but there's historical reasons. Because we used to do this in software. Now we do it in hardware inside of our MMU. So now we're going to be talking about a much more complex MMU. It's going to get nasty. And we're going to have massive